unfortunately, with no coherent phase detection, we cannot claim this is coherent lensing, but there is a correlation present. And what we interpret this correlation signature to be is that in a possible two-screen lensing system, one of the screens is unresolved and is creating the scintillation, or the scintillation screen is the one that's consistent and has an unresolved point source to the other screen. Of course, without phase coherence, the argument for plasma lensing is only going to be a morphological one. And so we're trying to actively see if we can get a lens morphology fit to this event. And so as a final note, I do want to highlight that with our simulation tool and trying to understand and analyze this event, we're developing the search methods and trying to understand the ways we might be able to detect coherent lensing candidates and identify them in data. And we're hopefully using this to find a gravitational lens event in the future. So stay tuned.
Thank you, Zarif. We have time for one quick question before we move on to the discussion session. Yeah.
Hey, Zarif, it's Lauren from McGill. I know nothing about lensing, but can one predict how many gravitationally lensed FRBs you should be detecting by time?
It depends on what type of lenses you think there are. Okay. And what type of so one of the, if you think that lenses are just like stars and whatnot, the chime rate is not enough to see it just yet. Mm-hmm. And the other one is if you think, you know, compact dark objects might compose of these lenses, then you get into the regime of like how much dark matter is compact objects, and that the rates can change. And I think the most optimistic is like 1 in 1,000.
Thank you.
Thank you all. Let's speak again.
And now we'll transition into the discussion session led by Mawson and who else? Seth. There you go.
Yeah. In Google Slides. We should activate this after we people speakers. Okay. All right. Hi, everybody. So this is the final discussion session and it's the final session for today, final discussion session too. And so that'll be on the cosmological applications. And so we've heard a bit about this throughout the course of the week. We'll have a few questions that we'll dive into, but it seemed prudent to kind of recap a little bit of the context, and so we're all on the same page. And so one of the first kind of questions that we want to address are, you know, how can we use FRBs as cosmological probes beyond the McGill relation that is fairly well studied. And so the reason we're interested is that FRBs clearly have demonstrated some power to contribute to cosmological problems. And so we want to see what other parts of the parameter space can we extend into. The reason why we think we can extend this further is that FRBs are pretty potent probes of propagation along the line of sight. And so we think we're really getting like impulse response function of the universe that can tell you a lot about what is going on over cosmological scales. Seems obvious that we can do cosmology. So kind of the big ticket items for things that we might be able to do, there are things like galactic feedback, which we heard from Isabel earlier, where, you know, different strengths of feedback blur or make very discrete the contributions to your DM and how much the scatter in your McGill relationship should evolve as a function of redshift. and how this correlates in with kind of known simulations in the power spectrum for some of these fluctuations. Another one is measuring the expansion velocity of the universe, where your Makar relation, the slope of this line that dominates the kind of average expectation is degenerate between the baryon density and the expansion speed of your universe. And so if you had some estimate of 1, normally we want to estimate the baryon density, but there's no reason that we can't also be simultaneously constraining H0 as well. Similarly, there's an approach to constraining expansion history using gravitational lenses as well. So this is called time delay cosmography. It's done by other teams in the field for kind of a semi-long time now, using multiply imaged quasars. With a variability in your quasar, you track in time the delay between the images, and that's dependent on the Hubble expansion. So similarly, we can time FRBs pretty well, and so we think that maybe this is a potential avenue. That same timing might let you search for gravitational lenses as a way to look for compact dark matter objects. And then finally, you might be able to also probe more complicated distributions of dark matter, where kind of this figure from Geraint Lewis's paper back in 2020 shows this idea where if you have some macroscopic image, like one of the images in your galaxy lens system, if it's micro-lensed by compact objects that are sub that scale, you might end up with an FRB that shows some gravitationally scattered profile that you might be able to use to constrain the power density, the density of fluctuations on the power spectrum of dark matter. And then finally, one of the other items is reionization. So we're measuring dispersion measure as a function of redshift. If we can really reach out in cosmological distances, we might be able to help constrain at what point the universe goes from ionized to neutral. And so here, at this point, I think that's kind of sufficient context to kick off one of the first questions for how can we use FRBs as cosmological probes other than their Makar relation? And I took the liberty of screen grabbing a few of Matt Quinn's slides from earlier in the week because they kind of address exactly this topic. Dylan. Yes.
Hello, this is Dylan Zhao from Stanford. I just wanted to give a little bit of context, I guess, because on one of your points you said FRBs have shown some potential for cosmology. I want to push back on the word some, right? The missing baryon problem was one of the major problems, open problems in cosmology, right? And essentially FRBs have solved this problem. So just, I think we are starting off on a more optimistic footing than I think we're giving FRBs credit for a little bit. In fact, I just Googled the missing baryon problem on Wikipedia, there's no mention of FRBs at all on the Wikipedia page, which one could solve. Maybe I could solve it. I don't know. But the point is that, you know, we've already made quite significant progress in cosmology with FRBs. And so there are many great things that we can continue to do, but I just wanted to point out that, you know, there's already, you know, there's reason to think that we could do a lot more than what we've already done. And also I wanted to point out, you know, Stella's talk, you know, if you looked at those plots, we're talking about using scattering to probe inhomogeneities in the CGM down to 1,000 kilometers, right? That's sort of this diffraction scale. That's incredibly tiny, right? No simulation is ever going to simulate down to those scales, right? So I just want to say that, you know, cosmology is interesting, and I think FRBs will be able to do a lot. Oh, I'm going to throw it across the whole row of people.
Thank you. This is Daniele Micheli from the Laboratory of Astrophysics, Marseille, France. And I'm very interested by the potential of fast radio bursts that are strongly lensed. So I wanted to do some shameless self-promotion, and because me and my group are starting this project called FLAME to try and detect the first examples of fast radio bursts that are strongly lensed with the upcoming core telescope in the next years.
Matt?
It's Matt Dobbs from McGill. Cosmology is cool. And cosmology consists of measuring the fundamental parameters in the universe. And we saw lots of examples of ways to potentially do that throughout the week so far. And then in many cases, we saw that the challenge of mapping our experimental results onto the theoretical expectations is even behind where we are for like how many FRBs we have versus redshift. It's really hard to do things like just map dispersion measure to redshift. And so when we think about doing cosmology with FRBs, I think we should be thinking not just about how we can measure things like the fundamental parameter of the universe, but also about how the astrophysics that we probe will feed back into the simulations to allow other people to measure the fundamental parameters of the universe. So as a key example, one of the things that CHIME does in other 21 centimeter experiments is that we're measuring the baryon acoustic oscillations. And as soon as we get to the fine angular scales, like the third or the fourth peak in the BAO, we're dominated by astrophysics effects that are probed by FRBs as they travel along the line of sight. And there's not much in cosmology today that happens with one probe doing it alone anymore. And we've really been thinking of examples like how can we do X or Y with one probe? If our probes, don't serve to measure something fundamental on their own, they might either constrain the astrophysics on those very, very, very small scales that are like wide open, ask 5 simulators what they think and they get 12 answers, or in cross correlation with other things.
Hi, Kiyo Masui from MIT. I just to follow on, I think one of the pleasant things I've seen in the literature since the last meeting in the 6 months ago was this shift from the literature trying to do this alone and say like measure the expansion rate, be supernova 1A, type 1A supernova, to talking about the power spectra in general, right? So these either indirectly through P of dm given z and mapping that to the power spectra, or these direct measurements of the power spectra through cross correlation analyses. And the nice thing there is that we're now talking the language of large scale structure surveys, right? And can really measure things. If we measure a power spectra, then the weak lensing survey can use those power spectra very kind of natively without using intermediaries of simulations or trying to disentangle that. So I think that the field has really come, in just 6 months has really come from trying to do it alone and trying to measure like the expansion history by itself to move towards what I think is a more symbiotic relationship with the rest of cosmology.
Yeah, I guess I just like to echo Matt McQuinn, University of Washington, some of these sentiments. And for my talk, I was defining cosmology as precision cosmology or dark matter. And I think you guys are going to do some really interesting stuff there. As Kiyo just mentioned, but yeah, there's FRBs are interesting. They're like coming into this like from this weird, different perspective that doesn't look like they a lot different than a lot of these other cosmology surveys. And there are questions that you guys are probing that are super interesting. Missing baryons being one. I mean, I think it's just like in this era where we're constraining things at the couple percent level, like the fact that we don't know where the baryons are in dark matter halos and around them at the order 1 level is like kind of crazy and interesting and totally matters for galaxy formation. And even things like why some galaxies are like not turning red and like not forming stars, and like there are big galaxy formation questions out there that you guys are helping to answer. And then one thing that was mentioned, reionization, which like I think we've seen a lot at this meeting, that there are like some really bright FRBs at higher frequencies that you guys are potentially gonna see that could see at high redshift. Like I guess there's no. It seems like they should be there if the star formation is happening at high redshift. We also don't have really good methods of constraining the reionization history of the universe. Our best measurements are the integrated Thomson scattering optical depth. And there's even like some controversy there that if you like change the Planck value, like like some of these controversies like evolving dark energy go away. But I could totally see like I think it would be super interesting to have a bunch of high redshift FRBs, either where you're finding the galaxy, or you could even imagine that like once they get high enough redshift, you're just these DMs are getting like crazy high, like over 5,000, like during reionization, and could imagine that the host galaxy contribution to the DM is small, but you can bound kind of the total integral of electrons through the universe, because even though you have some host galaxy contribution, like it's giving you an upper bound on on this electron column, and that's constraining the same thing that the CMB is constraining, and I think that's like super interesting. Okay, that's a lot. Sorry.
Hi, everyone. Calvin here from UC Berkeley. I'm going to disagree that FRBs are unlike anything else. They are actually they're actually very, very similar to weak lensing. So weak lensing measures all the matter. FRB measures all the electrons. So everything you do with weak lensing, you can do with a smaller number of FRBs because of the way the different noise and signal contributions work. But we have a recipe to follow, and that's whatever the weak lensing people are doing. And we should really be looking into that literature.
I think there's a contribution from online as well. Liam, would you like to unmute and say something?
Yeah, just quickly following up on the reionization stuff. It's amazing. Like Manisha talked about this Redshift 2 FRB. The rate, like the brightness of that source at Redshift 6, assuming a flat spectrum, is only 10 times lower, right? And I think DSA 2000 SK would probably detect something like that. Obviously, it depends on like delay time distributions. If FRBs are from old objects, then maybe it'll be hard. But yeah, I think we probably will have a pretty good sample of very high redshift FRBs in the not too distant future. And the question then just becomes, how do you optimally follow them up and ask JWST for 20 sources or whatever?
Kiyomizu, MIT again. Is there actually, and JWST gets redshifts of high redshift galaxies all the time, but those are optically selected and therefore intrinsically, or infrared selected, and therefore intrinsically bright galaxies. If you're FRB selecting galaxies, or any chance, like the average star, average, star formation rate weighted galaxy at redshift 6, is there a chance of getting its redshift even with JDub?
It's a good question. I don't know.
I think there's a good chance.
Matt says he thinks there's a good chance with JWST.
So do we have anybody in the audience that thinks that they've got an additional cosmological problem we might be able to contribute to that hasn't been talked about so far?
This is Sachin from McGill. My question is, if we want to probe reionization, we need something like 6,000 plus FRBs from those redshift that range from 6 to 9 or something. And how realistic is that we'll be able to, with the localizations from DSA 2000 or code, actually able to follow up that deep? I mean, like, and find the host, have the host association. Somebody.
That number sounds
Yeah.
way bigger than what I recall from Paz Benyamini and Pao and Kumar's paper. Do you mean unlocalized, where you don't know anything about the redshifts?
Yeah, they need the redshift information. This is a paper from folks from MPIA Heidelberg. I forgot. Yeah, it's a recent paper, 2024 paper, where they did some simulations, and you need the temperature. Yeah, they have. Yeah, I don't know I can't explain the details in detail, but
This is Om Gupta from UT Austin. So you only need order 100 FRBs with Redshift to probe at least to first order how reionization progressed. But you can, if you have a lot of unlocalized FRBs on the order of 10,000, then you can just do with that also. Yeah, but localized, you just need 100.
Hey, Daniele Michele from Marseille, France. So to answer Moson's question, to answer Moson's question about how to use fast radio bursts as probes that have not been published. I don't have a good answer about cosmology, but I think that some more thought could be put into use them as astrophysical probes. For example, in the context of strong lensing, we could get incredible results about the lens itself, as Moson hinted in his slides. And one example is the granularity of dark matter, which is something that many experiments around the world are looking for. And with the small scale that we can probe with fast radio burst, we could start looking into that.
Yeah, I can completely echo that statement. The best part about FRBs for this is that they're by and large the most angularly compact sources that we have, right? And so your lensing is sensitive to the size of that angular source. And so by having these very small sources, you're probing a regime of like clusters mass that is well beyond what other people can do.
Yeah, exactly. And this is just an example. You can, study things in the lens that are way beyond any other probes in terms of angular scale. You could measure single stars in there, study the luminosity function with a resolution that has never been probed before, and whatever source there you may find interesting in small scales.
And so that probably leads fairly well into our our second-ish question, which is like kind of in a sense tied into the first, in like highlighting which ways FRBs are actually kind of distinct as probes. What ways can they be competitive with other methods? And I think we've heard a little bit from people in the room about just this, in that FRBs are providing a complementary probe of the kind of things out there in cosmology on small scales that are otherwise unable to be kind of distinguished. And so it seems like we can be pretty handy in this area. Don't know what further comments people had.
I mean, here the obvious one is gravitational lensing. There's just nothing that can compete in this timescale that ever will exist. And so like we need more FRBs so we can find that first one and then go further into it. We need to extend the range out to which we're reliably measuring FRBs so that we have more lenses in the way of the ones we're seeing. And we know exactly how to do this. We know why we have biases there, so that we have a greater chance of seeing gravitational lensed FRBs. That first one's going to be like the most valuable, and then it's going to just build from there exponentially.
Yeah, so we'll go to Liam in a second, but to put a final comment on that, I guess I expect the first one, like breaking the ice in a way that is pretty definitive, I think will convert a lot of people to exactly this domain, because it will be really powerful if we can do it as we expect. Yeah, Liam, did you want to?
Actually, if there are other comments on that, then don't let me interrupt because.
No, I think you're free to.
Yeah, I agree. And relatedly, so obviously there's dispersion and scattering, which are really exciting, but then just the coherent nature of FRB. So I would love to hear people's thoughts on like how to practically take seriously this idea of space-based VLBI and measuring the geometry of the universe with repeating FRBs. I feel like only a very small number of people have thought about this carefully. Basically, Matt and his collaborator, or student, I'm not sure. But yeah, like how do we find these high frequency repeaters? What is the optimal strategy for mapping those out? They should be kind of local universe-ish. We'll probably detect them at lower frequencies and then just hope that they're broadband. Yeah, what do observers think? What do instrument builders think?
Why do you say we have to see them at lower frequency?
My thinking is just that you kind of want an all sky monitor, or you want something with an enormous field of view, which pushes you to low frequencies. And if you're building an aperture array, then you get lambda squared in collecting area, so you build a burst or a chasm. And even if you're in a dish, at 6 gigahertz, you don't have a lot of field of view. So blindly detecting repeaters is hard.
But I mean, the storage that's already worked is just like look for more R1s, right? There's like R1 is already in the source list, right? It's discovered. It's you can see it at 8 gigahertz. Those are the and it's at redshift more than 0.1.
Yeah, that's a good point.
So I mean, like we just rather than like we just keep doing what we're doing and then follow them up at higher frequencies to see if they're there.
Yeah. Okay. So just more L band or 600 megahertz FRBs, and some of them will be broadband.
Yeah. Wait for them to go hyperactive and then follow them up with GBT, right? Or fast or something with a high frequency receiver.
Yeah. I mean, they need to be bright because you only get the geometric mean of the thing that's in space and whatever's big on the ground.
So a fast size ground station is also key here.
Maybe on the moon.
Yeah, and about the repetition, I think we need to get better to find subsequent repeaters. And I think that for these instruments like DSA 2000 will be a great support because you need a lot of sensitivity and a lot of field of view to observe many sources at once, because no big dish is going to give you hundreds of hours to follow every single fast radio burst. So I think that in this sense, DSA 2000 may really change the field.
But actually, won't Chord be better for this? Chord will find FRBs with like 5-to-1 radio bands. And so you'll just assume, well, if it's 300 to 1500, then of course it's at 3 gigahertz.
Well, I was just thinking about your paper that says that you want a follow-up telescope that has the highest possible sensitivity with respect to the discovery one. So I just think that DSA 2000 can leverage its very high sensitivity.
Right.
I think Pavan had a point over here.
Hey, Pavan from Swinburne University. So I was just following up on the observer point of view. There are examples of radio telescopes which have been put in space just because they wanted to escape ionosphere for very low frequency observations, and there is precedence for that. So I was just curious, what sort of baselines would you be thinking, and in terms of having an instrument with in orbit or something like that, the what is the thinking of having the optimal frequency to be? Because we've seen a couple of hyperactive repeaters showing fairly broadband behavior in S band and L band as well. So yeah, just in terms of the temperature of the room.
I think in terms of baseline length, I don't know why there would be an upper limit per se. I suppose it becomes hard in the interstellar medium with some kind of helio correction for the changing kind of plasma environment, but probably that will get difficult on short baselines anyway.
I want to go back to a point that I'm not sure if we've explicitly said, but the simple fact that it's really hard to catch the second, third, or fourth image of a lensed FRB means I think you do have to go to some telescope design where you see the whole sky all the time. A coherent all-sky monitor is what we need.
And in terms of that as well, actually, in terms of strategies to be used, if you have, I think there are some domains where this becomes easier, in that if you're looking at one of these galaxy lens systems and you already have from the what you can see from the galaxy some kind of estimate of what the arrival time should be, but not pinned down to a very large accuracy, you might be able to point your instrument in some expected window where you think the burst will arrive. And then as in terms of detecting it, if the coherence is preserved, you should be able to detect these bursts down to a much finer signal to noise ratio by correlating the voltage data for the burst you already observed with the incoming stream to look for the lensed copy. Now, that is a pretty strict requirement for preserved coherence, but not between galaxies, but for stellar mass black hole systems, maybe.
Within your delay, sorry.
There's a regime where the delay is outside our window, and we could be finding subthreshold bursts this way, I guess.
Did you want to say more, or?
Just that the time delay time for these small objects they're still in our beam. We have time crossings that are, up to minutes to hours, and in some cases, the North Celestial Pole all day. But even in the 20-minute zone, the objects that we're talking about, being that size, have delays that already fall within our beam. What we need is more beams, more computing power, so that we don't miss that second flash. And the ones that are 3 hours or 4 days or 6 years away, I think they just aren't going to maintain the coherence.
Yeah, for galaxy lens fast radio burst, our strategy will be actually to, as Morton said, to predict when the second image will arrive. So with missions like Euclid, you can have a pretty good time window where to look for the second image, and then you can just use telescopes around the world to continuously look at that field. And if you have VLBI, you will see the two images arriving with a separation of about an arc second and about a week delay. Yeah, I think that with telescopes like CORD and DSA, which have a limited field of view, predicting where the future image will arrive is the only way to actually detect it.
Yeah, seeing an offset.
And seeing an offset is a smoking gun.
Yeah. And that's easy comparatively.
Vicky Caspi, McGill. One thing that, well, you asked a question before, so it is, I'm changing topics a little bit, but, you know, what are other potential cosmological applications? And one thing we didn't really hear much about, but I'm not sure why, and maybe it's because actually you can't do it, but magnetic fields in the universe, you know, RMs are very easy to measure with FRBs, and we've heard some talks about trying to model those, but aren't there interesting questions about how magnetic fields are generated in the universe and evolve, and could FRBs not be helpful for that?
I expect the obvious answer is yes, but let's hear from you. Nice.
I mean, I think that the Kiyomisui, MIT, the argument against that has been that quasars are so much more abundant, and they're like FRBs are less special, and that I can measure RMs from many, many different types of sources. And there are many types of sources that are much more abundant than FRBs, and with DSA 2000, it's going to be, you know, it's going to be wild how many non-FRB RMs will be available. Now those are those are all from the nuclei of galaxies and stuff like that, right? So then maybe there's some special niche why FRBs are better for in some way, but the naive counting sort of says that you should do better with another source.
Jason, I think behind you.
Hi, Ayush Pandey, University of Toronto. You get DMs, right? So you get magnetic field strengths for free. You can trace like magnetic field strengths in spiral galaxies out to whatever redshift you can detect them. Obviously, dealing with the fact that you have to know DMIGM, RM from the host galaxy, and so on. Like you have to be able to constrain those uncertainties, but yeah, you don't get DMs for AGM.
Yeah, Daniele McGill again. On this, I actually have a question. For the IGM, do you expect the net RM to be 0 due to random configurations of magnetic fields along the way? Or do you expect cosmologically some net value in one of the two directions?
I think Brian Gainslow, UC Santa Cruz. I think for the ability that we can actually measure RMs beyond ionosphere and systematic effects, the IGM mean RM should be 0, but the scatter should increase as you go to higher redshifts. So if you have a sufficient number of FRB RMs that are not contaminated by the hosts and at a range of redshifts, then you should be able to see the statistical signature of the IGM.
We have a comment from Liam.
Actually, more of a question, less of a comment. For Brian, so is it the case that like if those cosmic magnetic fields are primordial, not astrophysical, they can kind of have arbitrarily large coherence lengths, and therefore you could actually have non-zero average RMs for some distances?
Yeah, I think that's right. But I think those fields would also produce RMs that are so small that you couldn't measure them. Like there'd be much, I think that they're, from memory, they're less than 1 radian per square meter.
Gotcha, thanks.
Okay, and we might move on to our kind of final question, which Seth was gonna give us the lowdown on. Yeah, sure.
Yeah, so just to give some context, so here I'm showing a plot from the first overview paper, Lin et al. And it does a nice job of displaying the current and future radio telescopes in the space of like field of view and SCFD. And you can see that, you know, in the next few years, we're really going to pass the 10 FRBs per day boundary. And these will all be, you know, well localized FRBs, sub-arc second localizations. So This morning we heard from Mawson on RB float, which was the first CHIME FRB outrigger detection across all 3 outrigger stations. Very soon we'll be seeing order 300 per year, less than 100 milli-arcsecond localizations from CHIME FRB. CHIME FRB sample, we're seeing FRBs primarily from a redshift of around 0.5, but some likely up to 2.0. Burst will soon be detecting FRBs if they haven't yet already, and expect to see 100 per year with arcsecond localization, more local universe FRBs for which we'll be able to obtain archival redshifts very easily. And then, sort of early 2027, CHORD is expected to be full in line, and we're anticipating order 3,000 FRBs per year. These numbers are sort of uncertain at the factor of 2. Although for DSA 2000, I have 3,000 per year. I heard Liam say earlier 25,000 per year, so maybe this is uncertain at the factor of 10. But yeah, even better localizations due to the wide bandwidth, and sort of pushing to smaller field of view, but deeper, higher redshifts. So I think with CHORD, we expect to detect handfuls of FRBs out to redshift 3.5 or 4. And similarly, DSA 2000 will be even more sensitive and probe even further. And then sort of on the 5-year time scale, we have SKA, which will move in that same direction. So smaller field of view, higher sensitivity, and higher redshift FRBs. But in the next couple of years, we're going to be having 300 well-localized FRBs per year, and then it's rapidly going to expand to almost 10,000. So I think, am I missing any samples? Are there any other samples we should expect in the future? And what are their biases for these different cosmological applications that we just discussed?
Sorry, Adam Dong, NRAO. It's excuse me. I just have a quite naive question. How are those estimates optimistic, on point, or are they pessimistic? Because I don't know about other experiments, but I know CHIME only localizes the brighter ones, right? And 300 means 1 a day or slightly less than 1 a day. So I was just wondering, yeah, how optimistic they are.
I feel like I took this from one of Shion's slides.
Okay.
Can you comment how optimistic this is?
Okay, great. It's pretty realistic. Yeah. So for people online, Shion said it's pretty realistic. Okay. Is it Calvin?
We should think of something collectively to do with. This is Calvin from UC Berkeley. We should think of something to do with all the FRBs whose hosts are not luminous enough to associate with the bursts, or for those FRBs which are so far that we will never have a hope of doing something. How do we classify those into well-defined subsamples without host information?
Hey, Daniele Michele. I think we may get a hint for that from, for example, the GRB community, right? It's not so different. So what are they doing with those sources? I am not sure, but probably ignore them. I don't know. They do cosmology with them, so they basically, Pesci law is saying they spend enough telescope time to follow all of them up and localize them. That's what you're saying?
Saying that they're not interested in being spawned with the PRBs, so the potential for use of FRBs is higher, right?
Okay, so yes, I'll summarize it. He's saying that they are allowed to ignore them because they're not used for cosmology, whereas we shouldn't. Is there a fair? Okay.
Sorry. I mean, it's Kiyomisui again. It's application dependent, right? Like what there'll be some of these things we just talked about where you need to catch all of them. I think Shion showed that in her the selection bias things that for these cross correlation analyses, it's okay if you miss them. And there'll be other things where you care about catching them, maybe because it's a bias, or maybe just because you don't want to miss an opportunity for when you have small numbers that are really contributing to your constraints. So I don't know if that you can ask that question outside of thinking about a particular application. So you develop the proposals for the measurements you want to make, and then you think carefully about what your requirements are for that measurement, and you have to do that measurement by measurement.
Oh, yeah.
Just another question that it'd be nice to have feedback on. So you see 300 per year with the outriggers, but of course we detect more like 2 or 3 per day with just chime. And so so that means, roughly more than half of chime FRBs, unless we can find a way to localize those two, will not have localizations. And so are they still interesting? I think for finding repeaters, 100%, we definitely we're not going to throw them away, but are there other uses for them?
So I guess like a case study of exactly this is when James some of the ZDM related things, if you're trying to pin down H naught or be it whatever cosmological problem, if you have a well-defined model for how you expect your FRB observations to go, and then you're calibrating that model with FRBs where you have all the information, the redshifts, the dispersion measures, what kind of galaxies they lie in, estimates like that. The unlocalized FRBs they're not no information, right? That's if you have a very large statistical sample, it's still boosting the ability to evaluate your model on reality. You're just marginalizing that value over the redshift axis. And so I think the amount that they contribute to solving a problem is certainly lower than the localized bursts, but there's still value. They're not like trash to be thrown away. It's still useful. I think Andreas had a.
Andrea Possenti from INAF, Italy. First of all, I am amazed by these numbers, which of course we all hope to become real in 5 years time scale. As far as the question what to do with this large number of objects, I'm hearing this question since when I started my life in pulsar astronomy, because after the first 100 pulsars, according to some of our colleagues, everything was over. So why bother of discovering more pulsars? And we understood that the larger the population, the more interesting the exotic objects are. And so why not expecting when we will have 100,000 FRBs to have some of these just grazing Sagittarius A star, or why not expecting to find some of these in very strange environment, and they will teach us a lot of things. So, of course, you cannot invest all the time for following up all of them, but keep on discovering objects, even of the same class, will certainly reward you a lot in the end. This is at least what we learned from pulsar astronomy.
Thank you. Guys,
Hi, this is Amanda Cook from McGill. So I think I'm just thinking about foreground studies because that's what I do. But I also think that the like super precisely localized ones will make the just large statistical sample a lot more interesting. Like I can imagine for the galaxy, if we want to map out like the halo, if I actually had a distribution to pull from to estimate their redshift, to estimate their host DM, then I can really use like the full sky exposure in these thousands of FRBs, but right now we just simply don't have that information. And so like statistical probabilistic statements about what the host and IgM contribution are kind of meaningless. So I think that things like that will be really interesting when we get a better feel for with the precisely localized FRBs.
Is there a question online? Okay.
Hi, Adam Dong from NRAO. I actually thought Amanda was going to say what I was going to say, because I was just going to point out Amanda's work of constraining the halo and galactic DM contribution, right? Like that's, as we've seen, important for cosmology things. And the non-localized FRBs can give you bounds on the galactic and halo contributions, which would then help with the other things that you can do with the localized ones. That's just my comment.
Liam, do you want to go ahead and unmute?
Sure, thank you. Just a follow-up question for Vicky and Keo and others. I mean, given you've already gotten over the hurdle of permitting and power and infrastructure at these sites, isn't the marginal cost of adding collecting area to the outriggers kind of low, and therefore you could reclaim all of your detections? Or is it not quite worth it with cord coming and all that?
So I think Matt wanted to say something, but I'm just going to give it to Keo really quick to make a response.
Foundations are infinitely expensive. Foundations. Concrete is so expensive. And steel. Yeah.
Response, it's Matt Dobbs from McGill. Response to Keo, foundations for small dishes are probably a lot cheaper. And we already heard a few days ago that we know how to build a telescope that is completely free from intermittent RFI. That is a larger outrigger, so we should do that. We should build the same scale in the outrigger sites and require consistent triggers between the two, so there can't be an RFI influence. Comment on those ones that don't have redshifts. Gravitationally lensed FRBs are the coolest thing ever, and every one of them is equal no matter what their localization is. We just have to look for that coherent lensing, and so let's keep collecting them all. Get more.
Yeah, I guess to circle back to the question that was asked at the beginning of the slide, which is, how should we think about future surveys and especially design with these cosmological questions in line, right? So we heard from Shion that selection effects matter, right? And DM dependent selection effects clearly are the ones that are most relevant for the measurement that I'm most interested in, right? So I think the people that are pushing individual measurements should think about their survey requirements, their sample requirements, and communicate those to the instrument designers, right? So we for that particular measurement, we've discovered that DM dependent selection effects are the ones we care about, and we have to find a way of either designing a search algorithm that doesn't have them or subsampling after detection in a way that doesn't have these DM-dependent selection effects, right? For that particular measurement. And if you are pushing some measurement, you should think about what selection effects you care about. And then you should think about, is there a detection method or a detection algorithm or a subsampling method that avoids that systematic error without decimating your sample size, right? So, so you know, we're just these instruments all are in various stages of development. It's not too late to influence the decisions they make. If you have a measurement that you're pushing, then think about selection effects and think about survey requirements and communicate that, right? You know, write papers saying, by the way, Cord, please don't have this selection effect and do, but this other one is okay.
I guess like on that point, something that we've thought about a little bit for the core design is that coherent dispersion, doing one correction and changing the baseline DM of your search is kind of free. You could have all the data that's ingested in your pipeline coherently dispersed to 1,000 and start your search there such that the best DM that you could find would be at 1,000, and then your DM dependent selection effects start to tailor off your distribution either side of 1,000. And so you really could be honing in on a particular window in dispersion space that you're interested in. And currently we pick that window to be DM0. And so kind of it's the wrong answer, and that we should, and so given that we're thinking about these configurable quantities, there's power for nuanced search strategies in the future.
This is Vicky from McGill. Just to come back to what Liam asked. So if you, you know, you would be limited by, so you could increase the area of the outriggers, but you're limited by the sensitivity of chime. But with more computing, you could have more beams and be more sensitive with chime and then detect more with the outriggers just that way. And it so happens we have a proposal to do that. And so if one of you is the reviewer of that proposal, please keep this in mind.
Yeah, I think we've got like a couple of minutes, so we're basically at time. So I think we've got like a minute or two. Okay.
It's Matt Dobbs from McGill. As we talk about these future instruments like Cord, we're talking about ways to extend them to do more, and exactly the things that Mawson's talking about, that Vicky's talking about, are choices that we're making because they usually cost extra money. Another question for folks: it seems to be within reach that we could have baseband buffers, sorry, Andre, that are hours long by putting them in new solid state drives instead of RAM. And so imagine you had a telescope, you had Cord, or you had chime. It was looking at a big region of the sky, and the entire astronomical community had up to 2 hours to tell you which few milliseconds to pull out of your baseband buffer. So when DSA 2000 or DSA 110 sees their event that we don't trigger on, they could tell us later and say, hey, grab that. How valuable would that be? The price tag is $590,000, we think, which is like the cheapest VLBI piece of machinery you've ever bought. How valuable is that? And like, why won't someone give us $590,000 extra dollars? Or would you rather have more collecting area on the outriggers so you get a larger fraction of them? Or would you like to have microsecond timing? Or, oh, there was the third one. Oh, or would you like to have the 2 experiments so that you could eliminate local RFI. I think maybe we don't have time to answer that today, but we are talking about our future experiments tomorrow, and people could vote or express opinions on all these ways to spend a tiny, tiny amount of money compared to the projects.
Great. Okay, I think we'll leave it there, I suppose. Thank you for coming along to the discussion session, and yeah.